That's right. So hackathon is I think they posted about it here, right? So this Saturday. And when did you already had to sign up, right? No. So sign up as soon as possible. I know they're looking for team leads, and I would expect that several people from this class should be team leads because you're the seniors or the upper division students. All right. So do that as soon as possible. Go here. Homework today was merge sort thingy, right? How'd that go? Was it?
Yeah. No, I ended up. Well, you guys just doesn't even fully work.
I ended up, yours doesn't work at all. Yours is in Python. All right, so shared memory array was, didn't we have an array in shared memory?
No, I don't think so. We had an array.
We had an int pointer.
Yeah.
Oh, so that's why yours sucked.
Yeah. Yeah. They spend hours upon hours researching.
Well, you should. Okay, so let's talk about that first. All right. So is what's this? So really the source of your data, like you didn't even get started with sorting. All right, so let's talk about why that is. So let me.
At least I'm not the only one that struggled.
Oh, but you struggled worse than.
Oh yeah.
Throw something.
Wait, throw something. All right.
Oh, that'd be hilarious. All right. So let me start with this. So I'm going to go over to our shared memory example here. So why don't we start off here with our shared memory and talk about the difference between an int pointer and an int pointer.
Okay.
So let's see, I have a signal thing right now. Actually, you know what? I'm just gonna bring it. I'm gonna grab.
Also, why does C use the same symbol for an int pointer as like multiplication? Use with the star. That just because somebody was like, do it that way.
Yeah, well, they're using it in different contexts though. I mean, because the better question would be, why do they allow you to put a space between int and pointer, int and the star? If it was always no space, like I typically write it, then it would say, okay, well, that's just the type. It's just part of the spelling of the type.
You can also put it on the front or the back.
I guess that doesn't sound right to me, but I'm not sure I tested it.
I think you can put it on the front of the variable thing.
Oh yeah, it might be like
Well, yeah, that's what I'm saying is you could have the space there. I don't think it cares where you have it in there. All right, so I'm going to grab my segment ID here. And here, I'm just going to do this. Grab those pieces, and I need this shared memory, right? We'll bring it into merge sort here. This slash. Okay. Then let me paste in the stuff I just copied so I can zig it around. We'll start it off up here. Okay. And then I want to comment out all this stuff for a moment. So we can just focus on the shared memory part of this. Make sure I have everything included. That's in the FC, NTL, ABCD.H thing. This guy. Okay. So right now we're just focusing on the shared memory part of it. And really what we're talking about here has very little to do with shared memory. It has to do with how arrays work. All right, so arrays require contiguous memory, right? Okay, so for instance, last time I had this, I'll just copy it outside of here. I defined an int pointer called AR, and this guy was the resulting memory address of calling memory allocate on this number of integers times the size of it. I wanted to hold, in this case, what, 10 integers? All right, so I asked malloc, that function, memory allocate, C's version of the new keyword, to go get me some memory, enough memory to hold 10 integers. And it gave that to me as a int pointer. So what is stored inside of AR? AR is an int pointer, right? What's stored inside there is the base address of that array. Make sense? The very beginning of the array. So it does point to a very specific, the first integer, the integer at bucket 0, but that then is followed by other integers. Okay. Now, in our current example here, I create my segment ID, but what I'm asking for is I'm saying, give me enough memory for a single integer. One integer. So this is going to be, this is 10 times the size of int, and the size of int is 4 bytes. I'm going to get 40 bytes of memory. This guy is going to give me 4 bytes of memory. So when I say shared mem here, even though the name of the variables are different, I could call this AR2 if I wanted to. This guy's an int pointer. This guy's an int pointer. They both point to an integer in memory. It just so happens, though, that this guy points to the first integer in a series of integers because I asked for enough memory to hold more than one int. Where this guy points to the first integer in a very lonely bar. Just a single integer sitting there where there isn't a series of integers after it. Okay, but C allows us to walk past the memory. So if some of you, when you were testing this, were getting like weird giant numbers, I think a lot of times that's what it looks like. It'll be like a weird giant number. It's because you were reading from memory locations that you never requested. It was telling you what was there, but go ahead.
AR is not in shared.
Correct. AR is a normal array. That's why I said a few minutes ago that this really isn't a shared memory issue. This is a how do arrays work issue. Because shared memory is memory, just like malloc returns memory. The only difference is, as we've seen earlier in the course, is that when you use malloc, it's giving you memory that belongs to the current process. So it's kind of like this local memory, right? Whereas, and so if you have two different processes, they all both have their own little world. They're kind of their local scope of memory they have access to. So they can have a pointer to the same place. And we've seen that happen where they both have the same memory address, but they're actually writing to different places because they're writing to their own little local world. Shared memory allows us to escape outside of that to the more global scope that both processes can now attach to and see. Okay, it's still just memory. It just happens to be where's the location of that memory and where is it accessible. Make sense? There's nothing special about shared memory other than its location. All right, so even though if I were to print out, so here I'll do a printf. %p \n. We'll print out shared mem. Probably would do this. I'll say shared mem looks like that. Shared mem. And then I'll also do AR. That guy looks like that. We see that we get two basically the same kind of animals, right? Memory addresses. Okay, they both point to an integer. Now, if I haven't actually put a value in either of these, I'll go ahead and do that. So after I have shared memory, I'll say star shared mem is equal to 4. And I'll say star, and actually this will be drive the point home, AR is equal to 5. So now I'll print out the value that I found at that address. And I get my 4 and my 5. No, not shocking, right? All right. So now what maybe should bother you a little bit right now is, okay, well, I know we only asked for a single int here. So maybe this makes some sense. I think before we stored what, a process ID inside of our shared memory. Okay. So fine, you're storing up the number 4, whatever, some int. But hey, this guy was supposed to be an array. What the heck? What am I doing there? Go ahead. Yeah, so this is equivalent to this, which is equivalent. And if you want to see why the original one worked, it's AR plus 0 star. Go to the base address, take 0 integer size steps, and set that guy equal to 5. Make sense? All right, so that's how arrays work. That's how arrays worked in Java. That's how arrays work in C#. They require contiguous memory. And what you get when you build an array is you get that base address, the very, 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 very beginning. But since you know you have runway after that, well, at least in languages that you probably like better, Java, C#, the array will say, hey, I have 11 elements. I may not have had those filled up yet, but that's what you have to work with. Where in C, you know, nothing necessary. We might actually, I'm interested. Will I get a segmentation fault where I just get nothing, or will it work? I'm just going to go to bucket 5. I'll take 5 integer. I'll go to the base address. I'll take 5 integer size steps. Let's just see. It's not going to give me the output that I wanted, but let's see if it crashes. Oh, I have the star on the wrong side. Sorry. Right. So it did run. Default value at bucket 0 was a 0. So now I'm actually interested. So when I go and print this out, AR, the value AR, this is what's going to be at bucket 0 of this. Yeah. So who cares? I mean, the size is 40. Yes. What I've done is I've put the number 5 at memory address 20, the 20th memory address, right? Okay, so I put it 20 bytes in. 20 bytes in, I put that that memory address, I put the number 5. But I'm only printing out what's at the address 0. So if I say, show me what's at 5. There's my 5 that I wrote there. Make sense? All right. So now what if I did the same thing up here? Shared memory might work differently in this. If I say +5 and make that guy a 4. Okay, doesn't yell at me. That makes me happy. Okay, great. So this is perfect. All right. So when I asked to attach to some shared memory, when I talked to the operating system, I only said, hey, give me enough memory for one int. All right. So I kind of like I bought a little plot of land. But then I decided, you know what? Yeah, I don't own the neighbor's backyard, but I'm going to build in the in the neighbor's backyard. So I only own bucket 0 of this single. I only own a single plot of land for holding one int, right? So if we pretend that shared memory is a base address, it's just an address. Calling it a base address kind of just implies that it's the beginning of a larger collection. This just happens to be that it's the beginning of a collection of one, right? But I'm going ahead and saying, look, I know I requested a collection of one, but you know what? I'm going to jump 20 bytes in and I'm going to write some stuff over there. Yeah, I know I don't own that land. I never requested that land. I didn't ask the operating system for that land. The operating system didn't give me that land, but I'm going to write there anyways. C lets you do it. And kind of lucked out here that nothing else important was living in that land, because I came in here and I was able to print out the value at bucket 5 in my shared mem, which is the same thing as saying star shared mem plus 5. Take 5 integer size steps off of the base address of shared mem and give me the value that you found there. So it gives me the 4. Go ahead.
Does it take whatever steps that you like determine, like predetermine, like if it's like a char or something like that?
Yeah,
would it take all char size
because
steps?
of that.
Okay.
Yeah. If I had told this, if I had kept this guy as a void pointer, we talked about that last time. If that guy stayed as a void pointer, then 5 would take the default 1 byte size thing. So a void pointer is probably going to be treated the same as a char pointer. Yeah, so it is important. If I say it's a void pointer, I could do something like 5 times size of int. Take bigger steps. If I wanted to kind of hop through memory, you know, hop, skip, and jump and only read part of the, because it's stored in binary in memory. So you can do some pretty crazy stuff, right? By reading only part of an int. Like you take the second half of one int and the first half of the next int, and you actually build a new int out of those by just taking like a 2-step or something like that instead of a 4-step. I'm not sure how useful that is, but you can do it. Maybe this is starting to show you why in Java they took away the special syntax for dealing with pointers. Pointers are fun, but pointers are dangerous, and we're showing it right here, right? The operating system gave me the shared memory I asked for, and I just spit in its face, and I just took 5 steps away from it, and I built some stuff there. I don't own that land. The operating system might hand that to somebody else, okay? Nothing's going to keep my neighbor from going out and back and knocking over the brand new barbecue I built back there. It's a nice one. One of the stone ones, you had the inserts you put in there. You can get really hot. Doing a pizza. Mr. Gonzalez is out there. But this is really, I think I mentioned last time that one of the common errors I don't remember if I mentioned it in here or I mentioned just to you, the segmentation fault. And I don't know if I've seen that with online GDB, but it's something you will commonly see in a C compiler when you have full control over the environment. But typically a segmentation fault means you just tried to access some memory that you don't own and somebody else owns it. Bad. You would kind of hope that maybe like Java would give you like an array index out of bounds exception or something like that, right? A little bit more like a better error instead of just segmentation fault. Something went wrong. That sounds like a Lippmann type of exception. Like we're not going to be that specific. All right. So in any case, this should be fairly fascinating to you, where we asked for memory of size for a single int Yet I'm going to throw some stuff 5 ints over, and it let me do it. And it let me read from it. I still have this. Actually, I'm interested whether void pointer is treated as a. It's not. Okay, so even though because I'm still setting it as an int pointer here, so it's actually taking its size of steps from this guy. If I set that to a void pointer. It doesn't like me dereferencing a void pointer. Nah. Go back to this. Oh, interesting. So even though this guy came out as a char pointer and I'm treating it as a char pointer, and when I say go 5 steps in, oh, actually, no, it's fine because I'm reading from the exact same place I wrote it. I didn't write it where I thought I was writing it. I didn't write it at bucket 20 at memory address 20 bytes in. I actually wrote it at memory address 5 bytes in. And then I read from 5 bytes in. It wouldn't work if I do it here.
Yeah.
Because now I'm reading from a different place than I wrote. But if I did it here, and this is actually good because that lets us explain this a little bit better. 5 times size of int, I wrote my 5. Read from 5 times size of int. Yeah, that's what I'm printing here, right?
Not you didn't multiply by the 7.
Oh, thank you. Did it on purpose. Nailed it. Okay. And this is where, so now the difference between those 2 lines. So let me just show those 2 lines again, and then I'll take your question. So right now, I want you to think about memory. Don't think about it as an array. I have a plot of land in front of me that's a certain size. I can put stuff in that yard wherever I want. Now, there's some places that make sense. Like if I'm going to store stuff in an int array, I want to put my first int at memory address, whatever the base address is. I want to put my next number 4 bytes later. So I have enough room for that first int, right? Then I want to put the next one 4 bytes after that, so on and so forth. That's the most logical use of that land. Okay, but what am I doing right now is I'm asking shared memory for a char pointer. I'm still getting 4 bytes of memory. Just because I say the word int right here, this guy right here boils down to however big an int is. And an int is 4 bytes, 32 bits. So I'm asking the operating system, give me 4 bytes of memory somewhere. Make sense? So memory is memory. Doesn't matter. I mean, when I'm saying size of something, I'm just kind of giving it a, like, I'm going to hold something there. I'm probably saying I'm going to hold an int. Give me enough room for an int, whatever that is in this operating system. Typically ints are 4 bytes. All right. But when I actually attach to that shared memory, attached to using that segment ID, I'm going to say, you know what? Because it's going to come out, shared memory attached is going to give me a void pointer. It's giving me a pointer to generic memory, memory that doesn't imply what you might store there. So I'm going to go say, you know what? Go ahead and treat that as a char pointer, which indicates that if I were storing chars in there, in C, chars are 1 byte, 8 bits, because they use the ASCII character set instead of Unicode. In Java, they're 16 bits or 2 bytes. So that means when I go to bucket 1, of a char pointer, char array, I'm going to only go 1 byte off of the base address. Bucket 2 is 2 bytes off of it, 3 bytes off of it, 4 bytes off of it. All right. So I requested 4 bytes of memory. I read it in as a char pointer. And now I'm going to go ahead and so this is a double whammy. I'm taking 5 bytes. I'm taking 5 char size bytes because that's the kind of animal I'm dealing with here is a char pointer. So I'm taking 5 char size steps off the base address. So the first 3 of those were legal, right? Right? I own that land, right? So my first 3 steps were still in my backyard. Then when I took step 4 and step 5, I'm in the neighbor's yard at this point. So I took 5 steps, 5 bytes off that base address, and I stored the int 5, which is 4 bytes. So I'm taking up bucket 4, 5, 6, and 7 of an array that's not that big to hold an integer 5. Make sense? So what does that tell you? Is that it says you don't actually have to store an int where it would naturally fall, but now you've given up your opportunity to use the special syntax like that. Because this is going to say go 5 byte size chars in. And when I print this out, I get a weird value. Why am I getting a weird value? Let's see, am I even at the beginning of it? So this is going to be 5 bytes in. This is going to be bucket 5. So I'll be only looking at the first byte of that 4 byte value. And the number 5 is what? What's number 5 in binary? Five in binary is a 101. Okay. Now, but ints are 32 bits. So I need 29. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Let's see, we got 6 there. That's why it's a 0. I just read byte 5. That's byte 1, 2, 3, 4, 5, 6, 7, 8. That's byte 6. That's byte 7. So I actually need to read byte 8. I think I did my counting right there. Oh, thank you. No, I'm still, I get it, I get it, I get it, I get it. Did it on purpose. No, hold on, relax, relax. Relax. So this is shared memory plus 5 times size of int, which is going to, so hold on, I'm writing my, I want to make sure this is compatible with what I just did, because I showed you this is number 5 in binary. But if I say size of int here, that's going to take enough steps. So I don't want to do that. I want to say shared memory plus 5 bytes is going to get me, I'm going to put a 4 there. So actually this value is that guy. That's a 4, right? Number 4 in binary, 1s, 2s, 4s place. So this is a number 4 with all these zeros beforehand. So that's what I'm actually going to put. I'm going to say whatever this base address is plus 5 bytes. I'm going to store the number 4. And what it's going to start writing there is, so right at the beginning of the 5 bytes, it's going to start writing 0, 0, 0, 0, blah, 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 blah. And only at the end is it going to get down to this, because this guy is of type int. When I go to print out the value I found here and I decide, oh, I want you to read an integer, I want you to read a decimal from memory, it's going to say, okay, well, I'm going to be reading in some numbers. And I'm going to say, okay, well, go ahead and read it in from shared memory at bucket 8, which will be 8 bite-sized steps in off the base address of my shared memory. And this is the number that starts at bucket of 5 bytes in. Is this going to get me to where my 4 is now? So this starts at 5 bytes in, because that's what I wrote there, at 5 bytes in. This is 6 bytes in. This is 7 bytes in. This is 8 bytes in. Must be one more 0 in here. So that should be 8 bytes in on our shared memory, which is a char pointer. I don't think so, because I mean the value for it is star shared mem. Let's just go +5. Let's make sure the value's there. Here's my 4. So that's if I go 5 char size steps in. I'm guessing the problem is it's trying to read a 32-bit, a 4-byte value from there. And it's bridging 2 sides. I mentioned earlier, you can kind of meld 2 integers together. Maybe it's not allowing me to meld those 2 integers together. It's just saying these guys don't belong. But in any case, treat memory as a big bucket of stuff, right? And how you choose to put stuff in your backyard is up to you. You can advertise the kind of stuff you want to store back there, and it'll kind of do this stuff for you. That's probably how you want to program. Probably want to say, I want to store this, so let me store that. All right, so let's go back to where this was still kind of correct stuff. So we have shared memory there. Get rid of that. Malloc there. This. Change this to a pointer. AR, so now we should be back to just 2 memory addresses. Okay, so shared memory, in this case, we only ask for space for 1 int, whereas AR, we ask for space for 10 ints. But when we print out the value of those 2 variables, we see that they are both just memory addresses. They are the base address of a collection of, let's say, at least 1 element, in which case shared memory actually is only 1 element. All right, that makes some sense? So in this case, what would we do? We would say we actually want to request enough shared memory to hold array size of size of int. Give me more shared memory. We're still going to just get memory addresses out of this. Okay, but now we own more land in shared memory. Okay, so if I wanted everything else to stay the same, I can just kind of name my shared memory AR. Go ahead and dump my malloc. Still have my normal array like I had before. That array just happens to live in shared memory. 10 bucket array lives in shared memory. So now I can go through and fill up my array with random integers. And then we'll go ahead and display that guy. And we don't actually free shared memory. We detach from our shared memory. So what is that? SHDT? Okay. Oh, got an extra. Okay. So there's our array of random numbers. No different than what we had before, except it lives in shared memory space, space accessible by multiple processes, than in just this process's space. Make sense? All right. So if I do nothing different here, and I just go ahead and call merge sort, and I do this, I get sorted values. Merge sort still works. I just happen to be sorting it in shared memory instead of someplace else. Make sense? Okay. So any questions about the memory stuff? Does that clear some of that confusion stuff up? No. Mm-mm. I actually think, correct me if I'm wrong, if I say save here, and then I say share, I think this gives you a snapshot of this code. And even if I go and change it, it won't, it'll still be this code. I'm pretty sure that's true. Yep. So I don't have to paste the code in there. I can give you that link, and forever now that link will be that. That code is my understanding. If I'm wrong, then it's I know Jason's fault and yours, of course. Well, why not? I can give you the dean's address to get for bullying. Like, oh, that's what I said. I'm give you the dean's address. I've never failed you. I just was a little rough around the edges. All right. So we're all good with memory now? Run it a few times. I just. Oh, okay. So you it disgusts me. So you want that? See, that's how you fight back. You fix your display method, it's disgusting. All right, what's up? I didn't. Here, you probably at least want me to kick it down after this one though, right?
Well, no.
Just so if I print it more than once, it'll.
Oh, yeah.
Ninja. All right, so then you want me to display it before or display it after? Ninja, we're good. Okay. Well, what is it working?
It's not working for me in some cases, but
The same code? I mean, like you literally just running my program?
no, but it's the only difference is that I'm using the like shared memory instead of AR that changed it. Oh wait, no, I'm doing mine with multiple processors.
That's what I mean. I haven't, yeah. That's, yeah. We were not at that point yet. Okay. So now we have the code from last class, but operating in shared memory. We're cool with that? Okay. So now what we want to do is we want to effectively go in and replace our recursive calls. Say, look, rather than us say, I'm going to pause myself and do something recursively, I'm instead going to spawn off a couple of child processes and have them go do the work. Okay, but my next step as a parent, this is kind of talking at the high level. If I'm going to say, okay, well, we're not dealing with a trivially sorted list, so I'm going to create, child 1 and child 2, and I'm going to say you deal with the left list, you deal with the right list. But now I'm going to sit there and wait because I need to wait for them to finish before I can do my next step, which is merging. That make sense? Okay. So, where am I at here? Merge sort, that's fine there. We can call merge sort originally. So merge sort helper is really the dude we're messing with here. Now, the thing we do need to remember, well, the thing let's explore this piece first. I'm going to just create a little sample function here. Void change shared mem. This will take it at pointer AR, and we will say AR at bucket 2 is equal to -25, something like that. A number that we definitely would not have gotten before. All right, so what we're going to do here is we're going to have the parent create, we can actually just have it create one child initially and have that parent have the child call change shared memory, passing in the shared memory, then have it the child finish and have the parent then display the array and see if that change was noticed by the parent. Once you forked, did the shared memory remain shared? That's the question, right? We'll display it twice. So I'm going to go ahead and say int PID is equal to fork. All right, so we'll say if PID is equivalent to 0, that means if I'm the child, and I'm going to need to prototype this, otherwise it'll scream at me. If I'm the child, I'm going to go ahead and call change shared memory, passing it AR. Else, if I'm the parent, I'm going to wait for all my children. Do I already have syswait up there? Include sys/wait.h, is that it? Okay. So if I am the child, I'll go ahead and try to change shared memory. And I think it's pretty obvious it'll change that, right? And then the parent's going to wait, and then the parent's going to call display array afterwards. Okay, so only the child will actually change the value. And we'll go ahead and call display array in there. All right, so the first time we display, it is when we only have one process. It should display a random sequence of things. Then we create two processes. We'll create a child process. If I'm the child, I'm going to go ahead and change one of the buckets to -25. I guess I didn't have to do it in a function, but I did. Then I'm going to display my array, proving that that did in fact get changed to a -25. Then this child ends. The parent's going to sit there and wait until the child finishes, and then is going to display the array. We want to see if that -25 shows up. Okay. The -25 did show up. My speculation was it wasn't going to, that the children would each have to attach to the shared memory. But actually what we've talked about earlier today would defend why this is working. And that is when we attach to shared memory, nothing changed. The kind of value we got back, the memory address we got back was not any different, right? It just happened to be a memory address that went outside of the local memory group. So that means that that pointer is as good as any other pointer So we actually don't need to attach a second time. So that's good. So what are we seeing here? Here's the parent. This is the child after they change it to a -25. Then the child finishes. And this is the parent displaying. And if we want to actually see that, we'll just do it like a printf parent. So this is what the parent sees after the fact. This is what the child sees after they changed it, just to kind of label those things. So original, child made a change. We see it. Child then dies. Parent picks up after the child finished, prints out, hey, I'm the parent, and then displays it again and says, oh, I noticed the change that my child made. So that means I do not need to attach to shared memory multiple times. So far, so good. All right. So that was us testing shared memory. We see that shared memory only needs to be attached to once, and that pointer is good for all the children. Okay, so now, right now we're back to we just have random numbers. So we'll go into merge sort helper. Merge sort helper is where we actually do the sort. This says if it's not trivially sorted. If it's not trivially sorted, what do? Well, we figure out where the begin and end of the first half is, where the begin and end of the second half is. Great. Now, right now, we're calling recursively merge sort helper on the first half. We no longer want to do that. We now want a child to handle that part of it for us. Okay, so we're going to say int PID is equal to fork. If PID is equivalent to 0, if I'm the child, I'm going to call merge sort helper on that left-hand side. If I'm the parent, I need to create another child for the right-hand side. If I'm the child, I'll go ahead and call merge sort helper on the right-hand side. Else, I'm the parent, wait for my kids to finish. So we'll do a wait null, because this parent can't go on and do its merge step until the children have finished doing their thing. Make sense? So we're going to take this merge code. And we'll put it there inside of our, right after our wait, all the parents waiting for the with very strange spacing. One might say disgusting. Oh, it's great. All right, so the parent will wait for the kids to finish. They'll do their merge step only on the portion of the array that they were currently focused on, because now we have all these child processes floating around, and those child processes are only working with certain areas of our shared memory. So we'll change the portion of shared memory that this particular parent is in charge of. Remember, this might not be the original parent. This is just one of the parents, because our kids can have kids too, right? So once this guy's finished his merge, he will end as well. So that'll be that original call to merge sort helper, which will also, that might be like this. This guy will finish for that child. The child will then end. And once both children of a parent end, this guy blocks until that happens. Then that parent will do their merge, and then they'll end. And eventually we run out of parents until we're back to the original parent, who will do their final merge. Returning here to main. Now, we have to think about who called what here. We made an initial call to merge sort, passing it our shared memory. That was from the original parent before we created any children. That original parent then made a call to merge sort helper, the first call to merge sort helper. This guy does not finish until the original parent returns. Merge sort helper then starts its thing, and children will call merge sort helper over and over again until they finish, but they never return to the original merge sort. That was the parent's job. The parent of the parent, the original parent. So once merge sort finally returns from the original parent, we should be able to display array. Am I displaying it in multiple places, or all the children need to die? Oh, they should die. Didn't I say they died?
Yeah, you said that. Yeah, I don't know, it doesn't work like that.
So if I'm the child, what happens here? So I'm the child, I call merge sort helper, that finishes. I drop past all this stuff. I hit the end of this guy. So it is keeping track that he was called from merge sort here. So after a child dies, we need to exit. After a child finishes this, we need to exit. Is there no output? Because that's what I was telling you before, is that if the children die before the parent, before their children finish, well, this should block.
I have what we have.
How did you guys?
Oh, this guy?
I know why it's broken. Lauren told me.
Implicit declaration. Oh, so hold on. First of all, it doesn't like the fork system call, so we're not calling children. So did I, what is fork in uni, blah, blah, blah? Food, is it just uni std.h?
Run with me more.
So we have a 0 there.
So it's sort of correct.
Well, right. So this guy is broken in the middle.
It's not so- oh,
Well, it's sorting correctly depending on whether or not it, so somebody is not finishing in time.
I have a question about it.
Go ahead.
Are you sure that 8 is on all children? If you look at it like
That's possible. You're right. That would seem to be the behavior they were dealing with here. So then a parent would need to, I mean, I thought waited on all children.
it would make a lot of sense, but
Okay, so then we just need to remember the two children, right? So from a parent's perspective, if I'm in merge sort helper, I'll say int PID 1, PID 2. This will be PID 1. This will be PID 2. So we'll wait PID 1, wait PID 2. The question is, what if one of them finishes before the other? Oh, hold on. Now it's working all the time. Seemingly.
I mean, if you wait on child 1 and then child 2, then if you are waiting on child 1 and child 2 finishes.
It'll be finished as soon as child 1. Yeah, yeah, that seems to be what it's doing. So that is interesting that wait null doesn't wait on all the kids, but I really thought it did. I wonder if you can put something else inside of wait. For the children with weight.
Yeah, they have a value that says wait, and in the parentheses, it's in status.
The status of its kids waiting. Yeah, I got you. So almost like treating the kids like it's a semaphore. How many kids are there currently left? Yeah.
Are you getting the one going warning the
Int pointer, but argument was an int.
It fixes it if you put an ampersand before.
Oh, because it wants the address of the well, yeah. So I mean, you read your error message. So this guy says, I'm expecting in the address of a process ID. I gave it an int, but it is interesting that it's still working, because that means it's saying, okay, well, you gave me the wrong thing. I'll just treat it like you gave me the right thing. So instead of me giving it the actual integer, it wants me to tell it, where did I find the integer? Where did I find the integer? Okay, so wait null returns the number of living child processes. So what she's saying is wait null like that boils down to an int. That is the number of child processes. So if I say, while wait null is greater than 0, if I have more than 0 child processes, wait. Okay. Seems to do it. Still don't like busy wait loops. This isn't necessarily a horrible problem. There seems like, well, although if there is a wait function that says wait for all children, it probably internally just does a while loop. So maybe it's not a problem. So what this shows is that the wait function actually returns an int, and that int is the number of living children. So as long as the number of living children is greater than 0, just keep waiting. Go ahead.
What's the difference between an ampersand?
The star. So ampersand is, so if I have int PID is equal to 5. Star PID will give you a 5. Ampersand PID will give you some memory address. This is the location of where PID lives in memory, not the location of the value stored in PID. This is actually a location of where memory is storing that variable. And then at that memory location, so a variable has to live somewhere. So we have this thing called PID, and I'm a variable. I know how to hold a value, okay? But I have to live somewhere. So the ampersand PID will be the ampersand stands for address of. So this will be the address of me, the variable, not my value, the address of the variable itself. That makes some sense? The address of the value stored in PID. See, it depends on the kind of value you have in PID. So in this case, if you're wanting to get you're basically asking, what's the address of this literal, the literal 5? You're not gonna be able to get the address of a literal because it's just built into the language, I guess. Otherwise, if you're holding something that's not a literal, it would be like an object type. It would be address type. So its address would be its value, the value directly. You wouldn't dereference it. So anytime you see that guy, I read that as the value at this address. Whenever I see this guy, although in this case, star PID is going to scream at me because it's, this guy is just an int. So star PID dereferences this memory address and gives you the value that lives there. So really this would need to be a int pointer PID is equal to 5, something like that. Although it would probably need me to do this. So I'll create a way to hold an int pointer. I'll store at that place the number 5. Go ahead.
This is probably a stupid question that we already talked about. What is the difference between
an int holds a number. An int pointer holds the address to a number, the address where a number will live. Yeah, so whenever you use the word pointer, we're talking about addresses. All right, so that makes some sense. I'm not sure which of these two I like better. Choose your poison. I historically, if I were choosing between these two, I guess I would pick the weight on the individual process IDs. I'm not a fan of busy wait while loops, and that's something left over from my Dungeons and Dragons, not my Dungeons and Dragons, my Double Dragon story. I've told you that they used busy wait loops and all the bosses came at once, and my brother and I cried. We used to be so good at that game, and that was impossible. That's it is. All right. So this guy should work now. All right, so that looks good for multi-process merge sort. So I'll save that. I'll share that, and then let's take our last couple minutes and talk about pipes. All right. I think we talked about some good stuff today, right? Lots of memory stuff, hopefully cleared some things up. All right, so I have some starter code for pipes, and I think I left it in the state I want to leave it in. I want to leave it in a broken state, but it'll take me 2 seconds to get it back to that state. What? Well, no, but hold on. But I want credit here because I've admitted I'm rusty. I've started with some code here for you, and I've already had it working. I was just experimenting with some other things, so it won't take very long. I just sent you the other code. Yeah, I will. Oh, you want it? Yeah, I will. Well, let me see what it's doing right now. All right. So, and this isn't real long code here. So let's just talk about what is a pipe first of all. And I think we've introduced it one other time, or at least I've said it out loud. So a pipe is a one-way communication channel. You can, I'm going to actually say, represented as a 2-bucket int array where each int is what's usually referred to as an FD. This is a file descriptor. Go ahead.
Did you talk about it in the context of like something?
No, well, that is also a true statement, but I probably, when we were just saying, here's the options for inter-process communication, I think pipe was on the list. Yeah, we didn't talk about any sort of like detail. All right, so and this is actually going to get us into a couple of side discussions. Have I mentioned POSIX in here yet? Or is that a gesundheit? All right, so a pipe, it's a one-way communication channel represented as a two-bucket int array where each int is something called a file descriptor. And this gives us some insight into something called POSIX. So Unix, Linux, especially Linux, modern day Linux is what's known as a POSIX-based operating system, POSIX-compatible operating system. So POSIX is a standard for OSs that basically says that everything is a file. If you were just to drop it down to its bare minimums, POSIX says everything in the operating system is a file. If you want to write to a device in Linux, you go to like /dev something, it's a file. You're writing to a file. That file is magically linked to a device, something like that. So POSIX says everything's a file. So really, when I say that a pipe is represented as a two-bucket int array, yes, it's an integer array with a bucket 0 and a bucket 1, and in each one will be an int. That int is actually the file descriptor for an actual file. So when we think about when we open a pipe, even though they're just numbers, those numbers represent this magical communication channel that is the file descriptor of this thing that's been generated. They're not just numbers. They're numbers that represent something else that the operating system knows. Like, oh, you're going to use number 7. Gotcha. It's going to bring over this, I guess it'll be kind of like the tin can with the string coming out of it. Okay, it's going to bring that guy over. So you just yell in here when you need to talk. All right, so whenever you see POSIX, that's what it's talking about. Basically, everything's a file. Okay. So let's at least start looking at this code here. So I just have a couple of messages here that we might want to send. These are just strings. Nothing special about them. So here's the starting of our pipe. So it's just a two-bucket integer array. Nothing crazy about it. This is when I read stuff in. I'm gonna, I just have another char array for reading stuff in. This is the maximum size of what I can read in. I can read in something that's 16 bytes big, just in this example. Go ahead.
Why are you not doing the?
Because I was just doing this quick example. Yeah. It works because I'm not leaving main right now. Yeah, but if I was passing this stuff around, I probably do want to. Although I wouldn't need to for this guy because it's literally just holding ints. I don't need to worry about the contents not traveling with it because I'm not traveling with memory addresses. But I would still stand by what I said before is if you want to create memory, create it. When you're done with it, destroy it. So this is our magic keyword, just like fork. I pass it my two-bucket integer array, and it creates the pipe. So a real thing, a communication channel was just born behind the scenes here, okay? Even though what this is going to do is this is going to fill this integer array up with two integers. It seems like that's very simple. Just those two integers are special. They're the unique IDs of actual files, which happen to be the endpoints of a real thing, of a communication channel. All right, so that's what this pipe command actually does. So the pipe command fills that guy up. Now I'm going to create a child process. If I'm the child, I'm going to go ahead and write. So I'm going to use the write function to write to bucket 1 of my pipe. So the pipe array has a bucket 0, bucket 1. Bucket 0 is where we read, bucket 1 is where we write. Okay. So what am I going to write? I'm going to write message 1, which was hello world 1. And this is how big it is. My message size is 16. So all these guys are 16 bytes. Then I'll just print out that the child wrote this message and here's the his ID, his process ID. The parent will read from that pipe and then say, hey, I read it, message received, just as a quick example. So Interesting. It wrote it out in backwards because of the speed at which IO works, but the read and write did happen in different orders. So child wrote hello world 1, they're 948. Parent read hello world 1, 944. This is the error I was telling you that I wanted to show. The parent tried to read something, which was actually the last thing that was in there, but then the parent died. And what have we seen before? When the parent dies, the child can't finish doing its thing. Clearly, the child finished writing because the parent was able to read what the child wrote, but the child died before it could write something out to the screen. Okay. So let's just call that our introduction to pipes. So what we're going to look at next time, we'll mess with pipes a little bit more, and we're going to talk about solving some problems using pipes. One thing I will mention, that was the example I was going to show next, but pipes do not block. So when you try to read from a pipe, it will not prevent somebody else from writing to the pipe. So that means if you need to do some blocking or you need to do some synchronization between reads and writes, we're probably going to need to look at something like signals or something like that. All right, make some sense? All right, I think I mentioned on Slack, the exam will be next Thursday, so we will talk about that some on Tuesday. I'll go through the slides and stuff, and then we'll talk about pipes some more. More than likely, though, the exam will cover everything up to what we've done today. We probably won't have pipes on the exam. Questions, comments, concerns, bribes? All right, I will see everybody later.